Hello, Geography 232 students. Welcome to week 4 of our class on analysis and modeling. This week we're going to be talking about multispectral imagery. Your lab will get into how to visualize multispectral imagery, how to change RGB channels and visualize data differently. And in this lecture, I will sort of reintroduce the concept. I touched on it briefly during week 1, and we'll get it more into the various signatures that are viewable through remote sensing sensors. So this week's lecture is multispectral imagery. This lab is called Assess Hail Damage in Cornfields with Satellite Imagery. And as I said before, it will allow you to explore multispectral imagery and to alternate the channels to see how the different bands along the electromagnetic spectrum appear through the RGB channels. All right, so we will first cover what is spectral imaging. I'll briefly describe the difference between multi, hyper, and ultraspectral bands, and multi, hyper, and ultraspectral imagery. I will talk about spectral signatures, what they are, where they come from, and finally we'll finish with band combinations. How do you alternate those RGB channels to view different combinations along the electromagnetic spectrum? So first, what is spectral imaging? So they say if a picture is worth 1,000 words, then a multispectral image is worth 1,000 pictures. Why is that? Well, because a multispectral image is more than just what you see with the naked eye. All right, so each one of those pixels is actually sensed in myriad different ways by different sensors. And so in each of those differently sensed pixels are layered upon one another, we can pull a lot more information out of an image than just what it looks like to the naked eye. And as we've already touched on in week 1 and week 2, we can look at vegetation health, we can look at ocean depth, we can look at bare earth versus vegetated land, we can look at urban versus rural territory, urban versus vegetated, and so on and so forth. So multispectral imaging allows us to see more than just what is visible with the naked eye, and allows us to really drill down deeper. So what is spectral imaging? Well, spectral imaging is it's a combination or a hybrid of spectroscopy and imaging. So spectroscopy is essentially, it tells us about the composition of an object or the surface via its electromagnetic signature. So a spectroscope looks at the composition of material by measuring and interpreting its spectral signature. And it does that by looking at the different composition, maybe the chemical composition or the radiance, the reflectance off of an object or off of the surface. And then because every single object or material or substance has a unique spectral signature, spectroscopy allows us to view something about an object or surface from a distance. And so there's that key term, from a distance. And as I mentioned in week 1, remote sensing is about learning about something remote from where you're at, learning about something at a distance. And so combining the two allows us to not just see what's there with the naked eye, but actually learn something about the composition or the material. So imaging tells us where something is, and spectroscopy tells us kind of what something is. So spectral imagery is a combination of both. It tells us what and where. Okay, so and just so everyone knows, obviously it's outside the scope of this class, but spectroscopy is also used to tell us about the composition of atmospheres of planets outside of our own, right? So if we want to see what the composition of the atmosphere is of, we'll say, Saturn, we can aim a spectroscope at the surface of Saturn and measure the signature that comes back, and we can find out what the oxygen level is, if there is any, methane, all the different types of elements that are in the atmosphere. So what is multi, hyper, and ultraspectral imaging? Well, what they all have in common is that each one of those is a collection of reflected or emitted electromagnetic energy from features or areas of the Earth's surface. So really it just comes down to quantity, all right, and detail. So multispectral imagery is a collection of at least 3 channels, or 3 layers in this case, R, G, and B, red, green, blue, and they occupy wide, separated, or discrete bands along the electromagnetic spectrum. Hyperspectral, in contrast, is hundreds of narrow and contiguous bands. So the number of bands goes up by a factor of 100, and that increases the precision and the level of detail sensed by the sensors. and ultraspectral is increased by a factor of about 1,000 from multi. In that case, it's thousands of very narrow, very contiguous bands, and again, it's just an increased level of detail. And there aren't too many ultraspectral sensors out in space. Hyperion is one. Electromagnetic imaging. How does the process work? Well, we can think of it as a 5-step process. So step 1, electromagnetic energy or sunlight is cast on an object or surface and reflected. Step 2 is that the reflected energy is then transmitted up to a sensor. Step 3 is that sensor captures the available energy or the radiance from the object or the surface, and it can be simply the RGB bands along the EM spectrum, those that are visible to the naked eye, or it could also be bands that are invisible to the naked eye, including near infrared, shortwave infrared, or thermal bands, or others. In the 4th step, that signal is quantized into a discrete value and put into a pixel. So essentially, the signature is collected and then given a numerical value, and we call that numerical value a digital number or a DN. And then finally, the DN is processed and visualized on display, your monitor, or put into an image product, so perhaps a GIS layer of some sort. So you can think of it as 5 steps. And here it is sort of in practice. So we can imagine that this image of the Earth's surface is the actual ground. The sensor flies over, maybe it's on a satellite, maybe an airplane or a drone. The radiance is measured and given a value or a DN, digital number. And then that digital number is then rendered on screen as a raster image. Okay, spectral bands. So just as a quick refresher, and I talked about this during week 1, spectral bands obviously exist along the electromagnetic spectrum. So the spectrum is a range of light energy wavelengths and their properties. They're generally measured in micrometers, which is visible there. And I have a little quick reminder down at the bottom. So within a micrometer, there are 1,000 nanometers. And so sometimes you'll see micrometers listed on electromagnetic spectrum. Other times you'll see them as nanometers. And if it's nanometers, you're going to see it in the hundreds. If it's micrometers, it's going to be 1 decimal place. So that's usually how you can tell the difference. And just as a quick reminder, gamma and X-rays are at the top of the spectrum. Those are the shortest wavelengths, infinitesimally small wavelengths. Then as you move to longer and longer wavelengths, you get to ultraviolet, visible, which is blue, green, and red. Then as the wavelengths get longer, you get to near infrared, middle infrared, far infrared, and then microwave and radio waves, which are the bottom of the spectrum. The wavelengths are very long, like the length of a football field or even longer. So after these have been captured by a multispectral image sensor, they are essentially put into different channels. So multispectral image has 3 or more bands, each of which is spectrally narrow and may extend beyond what the human eye can see, as we've talked about. Color images have 3 bands, red, green, or blue, and they mimic the way the human eye sees. But as I've said before, remote sensing satellites can also sense outside of what the human eye can see, and we'll use infrared for an example. So when displaying an image, the display monitor, your computer or iPad or something, only has 3 channels to view light, R, G, and B. The RGB channels can be mixed with non-visible light bands, for example, near infrared, also shortwave infrared, or thermal. So those bands can be swapped around to display the surface or the object differently, and that's what you'll be doing in this week's lab. So here's just a couple of examples. In this case here, these are the RGB, the 3 typical segments or bands along the electromagnetic spectrum that we associate with natural color. Okay, so in this color image here on the bottom left, if we break it up into its 3 channels, we see that the red occupies between around 600 to 700 nanometers, green occupies between 500 and 600, and blue is at the lower end between 400 to 500. So for normal color images, the sensitivity of the camera is like that of the human eye. So it sort of emulates what we see with our eyes. Alternatively, we might use some sort of color infrared camera, in which case we would swap out that channel for infrared instead. So we have green occupying between 500 and 600, red occupying between 600 and 700, and Near infrared or infrared occupy between 700 and 800, which is outside the segment of the electromagnetic spectrum that we can actually see with our eyes. So if we compare the two, we see that blue has basically been removed, and instead we've kept green and red and supplemented infrared instead. So for color infrared images, the sensitivity of the camera is shifted toward the infrared spectrum, and it's useful for showing healthy vegetation, objects with more moisture content, things like that. So this here is how the red, green, and blue channel have essentially changed from displaying the RGB bands to infrared, in this case color infrared, the red band and the green band. So instead of red being with red, we've changed the red channel to infrared. The green channel has now become the red band, and the blue channel has become the green band. And the band numbers are going to depend on the sensor that was used to collect the imagery. I've got a slide here toward the end of the lecture that shows you Landsat 7 and Landsat 8, but there are other remote sensing satellites that are popular as well, including the European Space Agency's Sentinel satellite program, Sentinel 1 and 2, and they have different bands as well. But it's really just knowing what the bands represent, and again, the numbers that are associated with those bands are going to differ based off of the satellite or the remote sensor that was used. So here we can see 4 bands, a 4-band MSI. This is representing Newcomb, New York. We've got the blue, the green, and the red, and on the left we see the blue, green, and red are in fact coming in through the blue to the blue, green, and red channel. So the blue channel represents the actual blue band, the green channel is presenting the green band, and the red channel is representing the red band. And the result is what we call a true color image, and it's true in the sense that it mimics what our eyes see. And on the right we see a color infrared image. In that case, we see the blue channel is now pumping in the green band, green channel the red band, and the red channel the infrared band. And here we can see infrared. So things that are normally healthy vegetation, like green trees or grass, they end up showing up as red. And the end result is that you can tell the difference between lush, healthy vegetation and non-vegetated or poorly vegetated surfaces. And this is obviously helpful for monitoring agricultural health and things of that matter. Okay, spectral signature. So as I mentioned before, every object that is sensed by a remote sensing satellite has some sort of unique signature. It can be the surface of Earth, or it can be an actual individual object like a leaf or a piece of wood or what have you. Right? So everything has a unique spectral signature. So materials reflect portions of the electromagnetic spectrum in unique ways, hence the term signature. So it's just like when you write your name on a check, or you sign for whatever, some sort of official document, right? It's your own signature. Well, in the same way, objects and surfaces have their own unique signature that only represent those specific things, those specific combinations of molecules, essentially. So these reflectance properties tend to be consistent over time, so they're dependable and a durable way of identifying materials. And I will also add to that, they tend to be consistent over space. And that's why when astronomers point spectrometers, spectroscopes rather, at other distant non-Earth objects like other planets and other stars, we can still find out what the composition of those surfaces and what those atmospheres are, because the reflectance properties tend to be consistent over time and space, which is really kind of a spectacular achievement, because if we want to find out what the composition is of, we'll say, Mercury or Saturn or Uranus or a distant star, Proxima Centauri or something like that, we can aim a spectroscope at those distant planets or stars and find out something about the composition. It's pretty incredible. So spectral signatures are unique to substances, gases, materials, atmospheres, surfaces, objects, things of that matter. And the signature data can run from visual light only, so light that happens to be within the RGB bands, between that 400 to 700 micrometer band width, or outside of that into shortwave infrared, near infrared, thermal, and other bands. The uniqueness of the signatures are often a basic assumption used in feature extraction and pattern recognition processes. Again, whether we're looking at an object on Earth or an object outside of our planet's atmosphere, we can still look for a recognizable signature anywhere. Okay, and this chart here on the right is showing you what the spectral signature of seawater is versus maple leaves versus lodgepole pine. Reference signatures can be collected in a lab or in situ. So what that means is that if we want to identify, if we're looking for a specific type of object, we can collect a signature in advance, meaning that if we have essentially a criteria. And then if we find objects that meet that criteria, we can say, yes, this is in fact substance A, B, or C. So we essentially get the signature of an object in advance. And then if we go out looking for the object, if we find that signature, we can say, there it is. On the other hand, we might not know what the signature is. So if we aim the spectroscope, or in this case the remote sensing satellite, at a surface, we can gather its signature then. So maybe it's a distant planet that we've never seen before, and we want to find out something about it. In that case, we would gather the signature, and then we can kind of compare it to other signatures that we know, and we can find out what the composition is. Lab collection under controlled conditions is often preferred to avoid the need for illumination modeling. So essentially, if we are already knowing what we're looking for, then we don't necessarily have to draw conclusions based off of newly gathered data. We can say that if object A meets criteria X, Y, and Z, then that object A is such and such, because we've already identified it in a lab under certain conditions. Two well-known open sources are the U.S. Geological Survey and the Jet Propulsion Laboratory. So they both have essentially encyclopedias of spectral signatures. So here's the collection of those 3 spectral signatures one more time. You can see that seawater remains flat throughout the entire range from 0.4 or from 400 nanometers or 0.4 micrometers up to 2.4 micrometers. So it remains the same. Maple leaves tend to have a higher signature value in that range between around 500 to 0.5 to 1.4 micrometers, and lodgepole pines tend to be a fairly low value from around 0.9 to 1.9. All right, so a little bit about color band combinations. How do we imitate the light that our eyes see? How do we create images like the one you see here, the sample of infrared images? So it all comes down to certain combinations of bands. One very common band combination is what we call the NDVI, the Normalized Difference Vegetation Index. What that is essentially it's used to quantify vegetation greenness or health of vegetation, and it's useful for understanding vegetation density and assessing changes in plant health over time. So with the NDVI, we can aim it at, we'll say, for example, the Amazon rainforest, and we can see areas that are of a rich dark green are healthy, well-treed areas, right? Areas that tend to be a lighter green or a gray or a blue are going to have less and less coverage, less healthy vegetation, perhaps have been clear-cutted or maybe even developed and urbanized, right? So how do we actually come up with this? It's an index, right? So essentially it's a ratio. So NDVI is calculated as a ratio of the red band and near infrared bands. So we take near infrared minus red and divide that by near infrared plus red. So it's the difference divided by the total. You don't need to know the ratio, but that's how we arrive at that. So this imagery is captured by Landsat 4 through 7. So again, if you go back to lecture 1, we talk about Landsat originally launched in 1972. Landsat 7 and 8 are essentially the standard now. Landsat 8 is the most current. Landsat 7 is still a highly utilized remote sensing source. So with Landsat 4 through 7, NDVI is calculated as band 4 minus band 3 divided by the sum of band 4 plus band 3. Okay, so again, that's near infrared minus red divided by the sum of near infrared plus red. For Landsat 8, the bands are shifted forward because band 1 is actually aimed at identifying ocean health and coral reefs and things like that. So instead of being bands 3 and 4 for red and near infrared, they move up to bands 4 and band 5. In that case, it's band 5 minus band 4 divided by the sum of 5 plus 4. But in either case, it's still looking at that near infrared and red values. And I've got a little cheat sheet here. You can see Landsat 7, Landsat 8. And again, there are other Landsat imagery sources and other satellite arrays altogether, like the ESA has their own, which is a really great one. actually slightly higher resolution. As you can see here, Landsat 7 and 8 are at 30-meter resolution from band 1 to band 7, band 1, band 7 for all of them. But band 8, which is panchromatic, which essentially is a collection of all colors with a digital number from 0 to 255, has a spatial resolution of 15 meters, which is higher resolution. And then with the ESA also has its Sentinel-1 and 2 satellites. It has a different resolution altogether. It tends to be slightly higher. All right, so that's normalized difference vegetation index. We have another index that you're actually going to be working with this week in the lab, and that's called soil adjusted vegetation index, which is a lot like NDVI, except it is essentially it corrects for the influence of soil brightness in areas where vegetative cover is low. So soil adjusted vegetation index is used to correct for NDVI. The SAVI is calculated as a ratio between the red and the near infrared values with a soil brightness correction factor, which is just, we use L for that. And L is generally 0.5. That's kind of a standard. And I'll explain why that is, the median value. And so what we do is we take near infrared minus red divided by the sum of near infrared plus red plus that brightness correction factor. Then we multiply that as the sum, or the product of 1 plus L. Again, you don't need to remember the summary or the formula here. You just need to know what the end result is. So L is the soil brightness correction factor. That's what separates SAVI from NDVI. The value of L varies by the amount or the cover of green vegetation. In very high vegetation areas, L is 0. In areas with little to no green vegetation, L is 1. So we use 0.5 because that is essentially a median value, which applies to most situations where you have some vegetation, some bare earth or developed land. When L is 0, that's essentially the same. SAVI is going to be the same as NDVI. So we tend to use 0.5 because, as again I said, it's essentially kind of an average that we can expect to see. I won't go over the formula again, but just know that there's a difference between Landsat 4 through 7 and Landsat 8 with regards to the bands to use specifically. Here's the cheat sheet once again. Then lastly, we have normalized burn ratio. This is especially helpful here in the Western United States, where wildfires are a common occurrence and essentially something we live with on a year-to-year or month-to-month basis. So NBR is used to identify burned areas and provide a measure of burn severity. It's calculated as a ratio between the near infrared and the shortwave infrared values. So it's near infrared minus shortwave infrared divided by the sum of near plus shortwave. Okay, so it's calculated the same way as NDVI, but instead of using red plus near infrared, it's red plus shortwave infrared. So again, you don't need to know the formula, just know that Landsat 7 and 8 have different bands associated with shortwave infrared and near infrared. And there's your cheat sheet. All right, and finally, I have essentially just a collection of band combinations for Landsat 8. If you want to sort of emulate those different views that you saw with the Esri Landsat viewer from week 2, or was that week 1, you can do that with these combinations of bands. So again, this is specific to Landsat 8. If you want to do this with Landsat 7, you can. You just basically subtract 1 from each of these values. Okay, so you don't need to worry about natural color. With Landsat 4 through 7, that's just 3, 2, 1. False color urban, colored infrared, those are all going to allow you to really differentiate between vegetation and non-vegetation. Agriculture, that's essentially kind of like the NDVI index. You've got several of these. And again, these are just for your reference, and these might prove to be useful for your final projects. Okay. All right, so with that, that concludes this week's lecture. If you have any questions, feel free to reach out via the discussion board or email. Have a great week. We'll talk to you soon. Bye-bye.